ready to show you some things about Newton's method, 4.9. First of all, why is his method useful? Well, it's a way of finding zeros of equations, so such as, x squared plus 3x plus 5, we could just solve it using the quadratic formula or completing the square, but you could also use Newton's method. He just helps us find the zeros or the roots of a particular equation. We could actually just use the calculator nowadays, so to be honest with you, we could live without Newton's method, but I believe our calculators are programmed to use Newton's method to actually find the zeros. But let's go ahead and go to it here. It'll actually, if I do it right, it'll end up being one of the easier sections that we cover. All right. Here's kind of the geometry behind the method, okay, kind of why it works, and also where the little formula comes from. Okay, so let's say we have this function and it's f of x, and we're trying to figure out what the actual root is. And as we look at it, we can see that the actual root is right here. It's actually I have it listed as r. So this is the actual root. But we don't know that, and so we do an educated guess, an approximation. And let's say this is our first guess. We think that maybe the root is x sub 1. And I'll give you a method for kind of determining how we could come up with an educated guess. So we use this point and we go up to, this is his method, we go up to the graph and we draw a tangent line. So I won't try to draw anything unbelievably awesome here, but let's say we draw this tangent line. So I go ahead and I draw this, and let's pretend like it's straight. And that would be hitting the graph right here. And that point, I think you'd agree, would be x sub 1 comma f of x sub 1. And then this spot right here on the graph would be, we would call it x sub 2. It's kind of our next approximation. So if we kept doing this, let me just go ahead and show you the geometry again. If I did this again, so let's say I think x sub 2 is my next approximation. So then what do? I go up to the graph and I draw another tangent line, and let's say it's this, and then I find the zero of that tangent line, which is right here. And so my third approximation would be right here. And then what I would do is I would take that and I would go up to the graph and I would draw another tangent line. And if I did that enough times, I would be this is my x sub 4. If I did that enough times, I pretty much be right on the exact zero. So that's pretty much his method. You just keep using the tangent lines, and you're finding the zeros of the tangent lines, or the x-intercept, if you will, of the tangent line. So that's a little bit of the geometry behind his method. You'll see when you get to some problems in the book that it really matters, what your initial approximation is. If you have a really bad initial approximation, you may never figure out exactly what the root is. So we'll kind of work on that in class. All right, a little bit more of the, where the method comes from. We start off, I kind of showed you a little bit. We start with the initial approximation, that's a guess of what the real root is. We draw a tangent line, which is what I did. The equation of the line, is point slope form. So it's y minus, whatever the y coordinate is. And you remember the y coordinate was f of x sub 1. And then equals, and the slope at that spot is the derivative. And then x minus x sub 1. So that's the equation of the tangent line. Well, what we want is we want to figure out the x-intercept of that. So because we want the x-intercept, I'm just going to make a note, we want the x-intercept, which is the 0, right? So we want the x-intercept. And if you want the x-intercept, you always, all the x-intercepts have a y value of 0. So we say y equals 0, so we would go ahead and plug in a 0 for the y. So if we did that, we have, this, f of x sub 1, so negative there. And then right side would be the same, of course. And then what I would do next is I would divide both sides by f prime. So I'd have x minus x sub 1. And then if I divided by f prime, I would have this. And then my last step is to add the x sub 1 over. So I'd have x equals x sub 1. It's a negative, right? So I added, so x sub 1 minus f of x sub 1 over f prime of x. And that's also x sub 1 as well, both of those. Okay? Now what we found there was the x-intercept of that spot, the x-intercept of that tangent line. So this is actually, this little x is actually the picture, that x sub 2. So if you go back, this right here, that's the x-intercept of that tangent line. So that's why we could just say that that's x sub 2. So if you get any of that, great. If you don't, you'll still live and be just fine with Newton's method, but kind of want to give you the, where is this general form coming from? And it's just, the point slope formula of the equation of the tangent line. Okay. All right, let's take a look at the general form. So this is Newton's method. If you want to find the nth approximation, you just, this is x sub n plus 1. If you want to find a certain approximation, then you have to use the one right before it, and it's minus, and then it's just f of, whatever that number is, and then we divide by the derivative, at that particular spot as well. So this will make a little more sense once we put it all together with an example. All right, starting with an initial guess of x sub 1 equaling 2, find the third approximation, x sub 3 we would call it, to the root of the equation x sub 3 minus 2x minus 5. All right, so the function that we're actually dealing with is f of x equals, oh, it looks like it's going to start causing me trouble, so f of x equals x cubed minus 2x minus 5. Okay, so we have to have a function, so if it equals 0, then we're just going to, make it a function. And then we're going to find the derivative, so f prime of x equals, and it'll be, usually be a pretty easy derivative to find, so 3x squared minus 2. And they actually already gave us a little bit of a guess, right? They told us to start with x sub 1 equals 2. We could do, if we wanted to find a good guess, we could do the intermediate value theorem. We could plug in like a, this is just, again, to get, where are they getting these guesses from? This is a sidebar, okay? This doesn't have to do with finding it. So what we could do is we could do f of 2, and when you plug it, when you plug a 2 in, you get negative 1, and when you plug in a 3, you get 16. So we know by the intermediate value theorem that there has to be a 0 in between 2 and 3. So, 2 would be a pretty good guess to start with. You could probably even start with 3. You have some flexibility with these. You don't have to be right on, or really sometimes you don't even have to be that close initially. All right, so let's go ahead and do the method here. So we already have our initial guess, so we're ready to find that next approximation. So the way it works is we say, okay, we're looking for x sub 2, and that equals the one right before it. So that was the form, it was x sub n. So that means this is the one right before it. So x sub 1, and then minus, and then f of x sub 1, and then over f prime x sub n. Okay? And so again, I'm getting that from this general form. This is the one that's right before it. I'm sorry, this is the, this is like my x sub 2, and then this is the one that's right before it, one less. All right. So let's plug in some numbers. So we got x sub 2 equals, and we said that x sub 1 is 2, and then minus, and then you actually just have to plug in 2. everywhere into the initial function. So that would be 2 cubed minus 2 times 2 minus 5, and then and then f prime of that same number, so we would plug 2 into the derivative. So that would be 3, and then that would be 2 squared, and then minus 2. So we do the math there, and x sub 2 equals, let's see, I got 2 minus, and then this whole part here gave me a negative 0.1. So x sub 2 equals 2.1. So that's my second approximation. And then I would just do that again. So I'm going to do my x sub 3 now. Actually, I need a new sheet. So I'm going to do x sub 3. So my x sub 3 would be equal to, I have to use my previous number, which is 2.1, minus, and now I would plug 2.1 into the function. So it would be 2.1 cubed minus 2, 2.1 minus 5, and then I would take 2.1 and I would plug it into the derivative. So 3 times 2.1 quantity squared minus 2. Do all the math there. X sub 3. I'm going to say that x sub 3 is approximately 2.0946 when you do all this on your calculator. Okay? So there's my third approximation. Well, good news, I'm actually going to show you a pretty cool way to do this with the calculator. So let's look at the next example. So use Newton's method to find the 6th root of 2 correct to 8 decimal places. Okay. So, we know we could do the 6th root of 2 on the calculator, but I'm not sure that we would get it correct to 8 decimal places, or 8 decimal places. So let me see, what would that be? There's 2 raised to the, like 1 divided by 6. What would probably get here? So, I don't know. Maybe it would be correct to 8 decimal places. I don't know, but we're going to use Newton's method. So what we have to do is we have to realize that this is the same thing. This is the same. I'm going to write this down. This is the same as solving x to the 6th minus 2 equals 0. So you have to kind of sit there and buy the fact that that would be the same thing. If you kind of come up with an equation that means the same. So if you solve that equation, you would add 2, and then you take the square root for the 6th root of both sides. So that would be it would be the 0 of this particular function. So we need that for Newton's method because it uses functions. So we would say f of x equals, and that would be our x to the 6th minus 2. And then f prime of x would be equal to 6x to the 5th. All right? So let's say we're unsure, what's our initial, let me kind of clean that 5 up a little bit. We're unsure of an initial guess, but kind of use a little bit of logic. How big do you think the 6th root of 2 is? Is it, we know the square root of 2 is 1 point something, so the 6th root of 2 is not going to be any bigger than 1. So we're going to use 1 as our initial approximation. So let's use x sub 1 equals 1 as the initial. Okay. I'll just write that as our initial approximation. Okay. Now, I'm going to show you how to use the calculator. All right, so let me grab my calculator real quickly. Okay, so for the y1, we plug in the function, and for y2, we just put the derivative in there. So That's what I did. And then go ahead and get out of that screen. And then we're going to just use Newton's method. And the first thing we're going to do is we're going to store our initial approximation for x. So whatever that initial guess is, go ahead and let that be x. So I'm going to say that we're going to do 1. So we're going to say 1. We're going to store it for x. Just press enter, make sure it's in there good. All right. So then we're going to set up Newton's method. Newton's method says you take that initial approximation, that's x, and then minus, and then it's the, remember it's the, what is it? It's the function over the derivative. Well, this is cool because all you have to do is you do the function, and then you divide it. So that's the function, it's y1. And then you go to varchs again, and you pick y sub 2. And then what you want to do is you want to store that answer as your new x. So you're going to store x, and then press enter. And so that's going to be your second approximation. So you make a little note, you know, that, whoa, you make a little note that, you know, hey, this is my x sub 2. And then you would just do it again. So you just press enter. This is sweet because you just press enter, and that's your x sub 3, which I just kind of wanted to write that one. So that was my x sub 2. Now this is my x sub 3. And then all I have to do is just keep pressing enter, and I keep getting better and better. So I keep getting better and better. And it says to 8 decimal places, so I just have to look at this and see, when I go to 8 decimal places, when do they stop changing? You know, do they keep staying constant at least to 8 spots? So I just keep going, and I believe I have to go all the way to the 7th approximation this time before I notice, you know, that it's going to be pretty accurate. So I believe this answer, I think it's the 7th approximation if I'm not mistaken. I think it's this one here. I'm going to go one more. Yeah, I went one more and nothing really changed. And so my final answer here, fix that out, would be, let's see, to 8 decimal places, I would say it would be 1.1224625, kind of rounded it, okay? And that turned out to be, for me, that was the, and should be for you, should be the 7th approximation. So x sub 7 is what it is. All right. Last example. Find the root, correct the 6 decimal places of this particular equation. Well, just like the last time, we've got to have it in terms of, you know, a function. So the function for this would be, you know, sliding it all to one side first. So we're going to have cosine x minus x equals 0. So the function we're dealing with is f of x, and that equals, you know, cosine x minus x. And then we just calculate the derivative. So the derivative is pretty easy to calculate. So that would be minus sine x minus 1. And I would just say, hey, let's use our calculator again. And let's just use x sub 1 equals 1 as an initial guess again. So, and that's all I did. I just used the calculator again. I did the store. So just to recap real quick, I did 1. I stored it for x, and then I did x minus y sub 1 over y sub 2, and I stored that for x. Okay? So I did that for this problem, and I got x sub 2 is approximately 0.750363 8678. And then for x sub 3, I got approximately 0.7391128909. And x sub 4, they were still changing, so I kept pressing enter. And then I got 0.851334. And then last one I think I had to do was 0.739085, and then 1332. It was pretty obvious at that point that I was correct to 6 decimal places. So whatever you want to say, but you're good. You're definitely good here, and so whether you say you're using the one above it doesn't really matter, but we're accurate to 6 decimal places. Okay, so good. I think that should do it for us.